And then acute torture and pain. Right. Any questions on how things are going? What you're meant to be doing? Who's finished Lab 6? Right. And who's made a start on Lab 7? Okay. It's the same two, is it? Nobody else is willing to say anything. Righto. So remember that I'm here to answer all your questions at this point in time. I did earlier today post solutions to the design system questions that are on the web. So those solutions are there. Pardon my poor handwriting, it's not particularly great, but I hope I captured it all. There's a bit of a horizontal line missing here, but anyway, I think most of it's there. But it is a bit scribbly in places, so I hope you can make head and tail of it. And the code for these designs is actually at the end of lecture 10. So this is last year's lecture 10 here, but you'll see that the code is at the end here, code for the problems 10.5, 10.22 and 10.12. All right. Are there any questions on these exercises? Has anybody managed to look at them? Right, so you don't really know what I'm talking about. It's not very good. So the nature of the exercises is similar to what you'd be doing in the prac exam, although the complexity of the problems is probably a little bit simpler in these exercises than it is in the final exam. I think as a good guide for the final exam, have a look at the practice practical exam here, which, as I've stated several times before, is an actual practical exam that was given a few years ago. So you can see what it's like. The general style is exactly the same as is presented here. So given the English language description of a problem, derive pseudocode, ASM chart, data path, refine the ASM chart, and then code it. Hopefully all within 2 hours. It is a tough exam, I know that. And I mark it reasonably leniently because of that. However, there is a hurdle, and I'm expecting people to get 40% of the available marks for the prac exam in order to have passed the course. So there are a couple every year that miss out on passing, even though they would have otherwise passed, because they don't pass that hurdle. So it's probably a good idea to get a bit of practice in. So these digital design problems that are in the exercises are a good practice. They're not, as I say, the same sort of complexity probably as the problems that I present. They're usually a bit more complex. This sample paper is representative, but it's probably a bit on the complex side. And so I figured it would probably be good as a practice paper for you. Are there any questions?
How would you advise further study for more complex design?
I don't know. That's a very good question. Let's have a look at those exercises. The exercises are a little bit they're very self-contained and therefore a bit simple. Yeah, I would say the Morse code finite state machine that you have to design for Lab 6, is it? That's pretty good complexity. And I think that the binary search in Lab 7 is probably a bit more complex and complicated, but it's, I think, sort of if you understand it and can get a solution out, then I think you're on the right track. Then the main challenge is doing it in a short amount of time, because 2 hours is not a lot. So you not only need to know what you're doing, but you need to be proficient enough at it to be able to do it smoothly without really thinking too much about it. Like, they're open book exams, but don't be deceived. That doesn't mean that they're going to be easier because you've got access to your materials. If anything, that sort of implies you need to know your stuff so well that it's really just there as a reference in case you need to refer to something. Not that you should be figuring it out during the exam, obviously. So you need to really be on top of it. Yeah, there's not that many exercises there, but if you have a look at the book, for example, there's a couple of problems that we don't cover in the lecture, I haven't covered. The sorting of K registers, for example, is worth having a look at. It's quite a complicated, it's probably more complicated than anything I'd give in the exam. Okay? I can't give you more advice than that. Challenge yourself. Think of simple problems, digital problems that you figure you could create a solution for yourself, and then try and do it. Go through the motions of pseudocoding it, ASM chart, data path, refining, and coding it. Okay. So these problems all have certain characteristics in common. They all have some data path operations, because otherwise you're not being exercised on that element, and they also require a controller, finite state machine of some form or another. Okay. Any other questions? All right. In that case, let's talk about implementation technology. All right. So this is a topic that in the third edition of the book is presented as, I think it's chapter 3, so it comes really early in the book. But it's a bit of a distraction from the main theme of designing digital solutions to problems. And I've noticed that even in the 4th edition, it's also been moved to the end of the book, which is where I treat it in the course, or at least I think it is. I had a quick look at it and it seemed to have occurred. Which is not to say what I'm going to talk about isn't important, but it's not essential to being able to design digital circuits, because you can abstract away the transistor level circuitry and the transistor level behavior, largely speaking, from what we're talking about. We're talking largely about switches that are either on or off. And as you'll see today, that means transistors that are either cut off or saturated. And they're 2 operating points for transistors, but they're not the complete story. So if you wanted to look at analog circuitry, then you'd be needing to know this stuff a lot better. But for digital circuitry, it's not that important, in my opinion. Well, a lot of it is not that important. We need to know some things that are going on in order to understand the underlying reasons for what we're doing, but not a lot. And so I hope I've covered it whilst we've gone along to the level necessary. But today I'm going to delve a little bit deeper and talk about the structure of CMOS logic gates initially. And that, in order to understand that, you really need to understand how metal oxide semiconductor field effect transistors work. So the MOS part there comes from MOSFET. And so I'll just give a very brief review of how they operate from the perspective of what we need to know. And then we'll look at a variety of technologies that don't just use CMOS, but actually originally are probably more TTL based, a different type of transistor logic. And then we're going to review the structure of programmable logic devices and finish off with looking at custom integrated circuit chips and how what their main characteristics are as far as what we've learned is concerned. So the material that I'm going to talk about here that you haven't seen before isn't examinable, is really just for deeper understanding. So in binary digital circuits, we talk about voltage levels defining what the logic values are. Logic 0 usually being associated with ground or a voltage of 0, and VDD being the source voltage or the supply voltage for our system. Typically being in the range of 1 to 5 volts, although for 7 nanometers it's getting a bit lower than 1 volt, that top supply voltage. And there's a range of values sort of between 60% of the maximum and the maximum voltage that are typically sort of associated with voltage level, a logic level of 1. And there's also a range down below. The lowest 40% of this voltage range is usually sort of associated with logic level 0. And if logic level 1 has a high voltage and logic level 0 has a low voltage, that's associated with or known as a positive logic system. And in one slide later on, you'll see the alternative, the negative logic system. Right, so gates are built using transistors, and these days that commonly is a metal oxide semiconductor field effect transistor, which has a number of different ways of diagrammatically representing them. These are common ones. I'm going to mainly use this method down here. And what we're interested in is the ability to use the gate voltage, the voltage on this, this terminal here, to control the current that flows between the drain and the source. And in N-channel metal MOSFETs, VD is high, VS is at ground. Current, as you know, flows in the opposite direction to electrons flowing, and we need a continuous path for electrons to be able to flow, or for a current to flow, and therefore for us to change the voltage at either end of this transistor. And that can be done by applying a voltage to the gate, as we'll see. An N-channel means that we form a channel between the drain and the source that's primarily composed of free electrons that allow that current to flow, whereas a P-channel transistor relies on holes being able to flow across that channel. So they have relatively speaking, a positive charge, whereas electrons have, relatively speaking, a negative charge, and hence N channel and P channel. Right. So I think, as is pointed out down the bottom here, there's a so-called threshold voltage, which we'll talk about in a moment and define a little bit more. And if this gate voltage is below that threshold voltage, then there's no conduction between the drain and the source. But if the gate voltage goes above this so-called threshold voltage, then there is a channel there which allows a current to flow between the two, and therefore we can the voltage at the drain and the source become the same. All right. So the alternative to an N-channel MOSFET is a P-channel MOSFET. Still has the behavior of a switch, which is either open or closed, which is all we're really interested in order to build gates. However, there's a few differences. Firstly, the source voltage here is usually a high voltage and the drain is low, and this is a source of holes now that are flowing in the same direction as the current is flowing. Usually the base or the substrate of the transistor is tied to the supply or the source voltage. So Vs is the same as VDD in this particular case. And therefore we have to pull the gate voltage low in order to create this channel for the holes to flow from the source to the drain. So source and drain refer to the source or the drain of electrons or holes respectively. VDD refers to the supply voltage. In P channel, the base or the substrate of the transistor is tied to the supply voltage. In NMOS transistors, it's tied to the source, which is at ground level, as we saw over here. So we see that the base or the body is connected to ground. So here, VG has to go low in order to attract holes into a channel region here before this guy will conduct, and it will only conduct when that voltage is lower than this so-called threshold voltage. All right, so let's have a look at this in more detail from the perspective of an N-channel MOSFET. So this is specific to the NMOS, but you have to flip the concepts around in your mind for the PMOS. So it really only requires you to remember one of these in any sort of detail to be able to figure out what happens with the other. So let's assume initially that there's no voltage applied to the drain or the source, so VDS is 0, and that we apply a small, remember that the substrate here is at ground, which is the same as the source, it's normally at ground. So when we apply a small voltage to the gate, that's effectively called VGS, because it's the difference between the gate and the source voltage. When we apply a small voltage to that, the oxide layer here forms a capacitor effectively in this region of the FET. And the substrate here, which is positively doped, which means in this particular case that it has ions infused in it that attract electrons. So the electrons, the free electrons, bind to those ions, and that leaves a surplus of holes, and hence it's called a P-type substrate. So when we apply positive voltage to this upper plate of the capacitor, electrons, both in the form of bound electrons and free electrons, are drawn into this region below the insulator. So there's a channel builds up of negatively charged particles on the bottom side of this positively charged plate, relatively positively charged plate. And of course that means they're drawn away from this region that's called a depletion region. Now as we keep increasing that voltage, VGS, up to a point called the threshold voltage, the size of this region, the thickness of this region keeps growing, and eventually more and more free electrons get drawn into it. There's still some free electrons left in this substrate. They get drawn in, and they then make it possible for a current to flow between the source and the drain by having electrons flowing towards the drain and of course the current flowing in the opposite direction. So at the point where VGS is greater than the threshold voltage, we have what's known as an N channel here that allows a current to flow between the drain and the source, given by the fact that there's a small voltage applied to the drain here. Smaller though than this gate VGS voltage, all right? So when this condition has been met, that VGS is greater than VT and VDS is lower than the difference between VGS and VT, we have this channel. Its thickness is defined by the difference between VGS and VT. So the greater VGS is, the thicker this region becomes. The thicker that region becomes, the lower the resistance, right? When these conditions are met, we have free electrons here that are flowing from the left to the right effectively, and therefore a current that flows from the right to the left. Now, there does come a point though where if you keep ramping up the drain source voltage, that we begin to see a tapering in this region over towards the drain here, because the difference between the gate and the drain voltage becomes smaller, and therefore there's not so much draw on electrons and free electrons in this part of the transistor. And eventually we get to a point that's known as pinch-off, where this ramp actually goes to zero at the drain side up here. And when that happens, there's no more capacity for electrons to be flowing at a particular rate through that channel. Effectively, the resistance is too great, and we get what's known as pinch-off occurring here. And at this particular point in time, it doesn't matter how much more you ramp up the drain source voltage, we're not going to get any more current flowing through the device. So effectively, we have this sort of behavior in this channel. Initially, the thickness of this channel is given by the difference between VGS and VT. And as we increase VDS, we get more and more, closer and closer to this pinch-off condition where we now no longer have a continuous channel going over to the drain. We still get some electrons jumping over the gap, but there's no more a continuous channel between the two. And that leads to a current voltage behavior that looks a bit like this. So in this particular graph, we have VDS along the x-axis and the drain current ID on the y-axis. Initially, when VGS exceeds VT, we see a relatively linear behavior here, where the current and voltage are proportional, given by the resistance of that channel, and the thickness of the channel is defined by the difference between VGS and VT. But as we increase VD, we get closer and closer to this pinch-off position where you can no longer increase the current, irrespective of the fact that we're increasing the voltage. Right? So while this region is called triode, where the transistor has this non-linear behavior, we actually are interested only in the saturated behavior of the device over here, or the cutoff behavior down here, where we don't have any current flowing through the device. Okay? So I hope that gives you a rough idea of how transistors operate, or how metal oxide semiconductor field effect transistors operate. So let's have a look again at the NMOS device. So the supply voltage might be a couple of volts. The source voltage is 0. When VG is equal to the supply voltage, then we've saturated that device and it's in this on position, and effectively that pulls the drain voltage down to the source, down to ground. On the other hand, when VG is set to 0, there's no current flowing between the two, and hence VD is high, VS is low, and there's a potential difference across this switch, right? PMOS has complementary behavior, as is indicated by the fact that we have a bubble there on that gate. The supply voltage is still high. The drain voltage is sort of floating here now. When VG is equal to VDD, this guy is open switched. It's cut off. There's no current supply because there's no. We're unable to establish a channel of holes here for the current to flow because VG is as high as VDD, so there's no potential difference across that capacitor at that point in time. But when VG is pulled low, then we get a closed circuit, and that pulls the drain voltage up to the supply voltage VDD. Okay? Right, and that's about all we really need to know to see how CMOS works. But before we do that, let's have a look then at some basic transistor circuits. This first one just uses an NMOS transistor in series with a resistor, a current limiting resistor, and a power supply. Now, who doesn't understand what the circuit symbols are here and how that's meant to be interpreted? Do you all understand that? So you all have enough physics and electrical engineering background? Okay, good. So this resistor here is really just limiting the current when we switch this transistor on, so that the current flows straight from VDD down to ground here. And because of that, there's no resistance really across the transistor. So effectively, VF is drawn down to ground when this guy short circuits, right? So when Vx is high, Vf is low. But when Vx is low, there's no path to ground, and so Vf is pulled up to the same magnitude, the same value as VDD, right? There's no current flowing through there. So hence it operates as an inverter. Vx is low, Vf is high, Vx is high, Vf is low, right? All right. A NAND gate can also be realized by just connecting two NMOS transistors in series, right? Now, both of these guys have to be on in order to pull VF down to ground, right? If not both of them, if we have a circumstance where they're not both closed, then VF is going to be high. So as we see here, when X1 and X2 are not both 1 or high, which leads to a low VF voltage, we have a high VF voltage, right? So that's the NAND behavior. Similarly, a NOR gate can be constructed by placing two NMOS transistors in parallel here, in which case either one of these being on, switched on, so high, leads to a path to ground and therefore pulls VF low, right? So as soon as one of these guys is 1, VF goes to 0. Right, so we can actually implement every one of these networks that pull VF down to ground. We can implement them using PMOS transistors as well. And it'd be actually a complementary circuit, as we'll see in a moment. But CMOS comes about, or this notion of having a pull-up network here to replace this resistor so that we on the one hand are either pulling VF up to VDD or pulling VF down to ground, replaces that that resistor, which reduces the power burn that we have here. So we no longer have any power being dissipated by virtue of current flowing through this resistor. So that's a really nice thing. And secondly, of course, if we can build our entire circuit just out of transistors, that's easier to manufacture than to have to manufacture a resistor as well as transistors in our chips. So that's a really nice feature. So let's have a look at what CMOS circuits then look like. So in effect, what we do is we implement a pull-down network out of NMOS transistors and a complementary, not the same, complementary network out of PMOS transistors to act as a pull-up network. And what we're going to do is we're going to drive our inputs the same way as we would normally do, and for each particular combination of input voltages, either the pull-down network will pull us down to ground, making VF 0, or the pull-up network will pull us up to VDD, making VF 1. Okay? All right. And in fact, the relationship between these networks are that wherever there's a series connection of NMOS transistors in the pull-down network, there's going to be a parallel connection of PMOS transistors in the pull-up network and vice versa. And that's about all you really need to know to be able to solve the problem. So without further ado, here's the CMOS realization of a NOT gate. Remember, we only had one NMOS transistor for our inverted circuit. So the PMOS is just the same, just a single PMOS transistor. And in this case, depending upon the voltage that we have on Vx, if it's low, then that will cause this PMOS transistor to saturate, which will pull Vf up to VDD. But if Vx is high, that will cause the NMOS transistor to close and saturate, thereby pulling Vf down to ground. And of course, when Vx is high, the transistor T1 is going to be cut off. It's going to be open circuit. Whereas when Vx is low, transistor T2 is going to be cut off. There's no path to ground. And so we either have a path that connects Vf straight up to VDD or down to ground here. All right? Hope that's clear. This is really nice because essentially we have very little current flow through this circuit in the steady state. So when Vx is either high or low, there's virtually no current flow at all. There is a small amount of leakage current across the gate, and that's not, we can't just ignore that. But the only other current that really flows in the device is the so-called dynamic power, which is when we get a change in Vx from low to high or from high to low, there's usually a small overlap between when these two transistors are either cut off or saturated. And so there is a short period where there's a short circuit, if you like, between VDD and ground. And therefore, that's when you get power dissipation in this. And this dynamic power, that becomes more of an issue the more transistors you have, the higher the clock frequency, and the lower the supply voltage VDD is relative to the threshold voltage, actually. Okay, so these are all nice characteristics as well for these CMOS circuits. Back to the NAND gate, we had two transistors in series. That implies we're going to have two PMOS transistors in parallel in the pull-up network. But that can also be derived, as explained over here in the text, by just considering the NAND function given up the top here. This tells us under what circumstances the output VF is 1. So it's going to be 1 when either X1 is low or X2 is low. And that suggests that we have to have we have to have two transistors in parallel effectively, because if there's an either-or situation, we want to have either one or the other being closed and therefore pulling the F up to VDD. We can also derive the pull-down network using the same expression. So the pull-down network has to implement the complement of whatever the function was for the pull-up network. So we had F as the complement of x1 and x2, so F bar has to just be x1 and x2. And of course that suggests that we have to have two NMOS transistors connected in series in order to get F to be 0. Okay. The NOR gate can be similarly analysed. Previously we had two NMOS transistors in parallel, which implies we need two PMOS transistors in series in order for the pull-up network. All right, okay, so this diagram here illustrates on the left-hand side here a NAND gate, and then that's followed by an inverter here in order to obtain the AND function for VF. So this is something that we discussed much earlier in the course, where I explained that NAND-NOR circuits are preferred over AND or NOT circuits because they're actually cheaper. They use less transistors. So we see a NAND gate needs 4 transistors, but an AND gate needs 6 transistors to be implemented, okay? If it's a 2-input gate. Right, what's this? This is a more generic problem. We have to implement this function. This tells us what the pull-up network is meant to be. So this suggests that we have one transistor that's in parallel with 2 transistors that are in series, right? So here's our X1 and here's X2 and X3 over the side. The pull-down network has to be the complement of this, so just using De Morgan's we can see that that has to be a single transistor in series with 2 transistors in parallel. So we see the dual or the complementary network down the bottom here. Okay, I hope that's clear. Any questions so far? All good? Right, I promised you I would talk about negative logic as well as positive logic. If you look at the data sheet for a small package that contains NAND gates, it will not list the truth table for the NAND gate. It will list a table like this that indicates what the output voltage level is given a particular input logic value, okay, voltage value. And that corresponds to the positive logic interpretation where low is 0 and high is 1. That gives us the NAND function for this particular circuit. But we can flip that around and think of low voltage as being logic 1 and high voltage as being logic 0, in which case this table is interpreted in this way, which corresponds to the NOR function. So the same circuit can be used both as a NOR or a NAND gate, depending upon your interpretation of what is low voltage and what a high voltage is, okay? So to indicate that a circuit is using negative logic, we put these triangles, these ramps, if you like, onto the signal wires, if you like. All right? Now, I'm not going to talk about this any further. Just be aware of the fact that data sheets don't actually use truth tables. They use these voltage levels, and that's because you might be using negative logic rather than positive logic to implement your circuit. All right, so now we're going to shift gears a little and have a look at how circuits have been implemented over time. And this is a bit of a throwback. I don't know how interested you guys are in any of this, to be honest. But for me, this takes me back to the beginnings of my knowledge of computers. So I suppose my life has sort of spanned the entire time scale that is discussed in the following sets of slides. And I dug out a picture today that I thought I would never see again, but I managed to find it. I'll show it to you in a moment. The first really popular common manufacturing for chips were these so-called TTL packages, this 7400 series package. And many of you will have seen them, if nowhere else than in our CSE computer museum. There's some circuit boards there that have these type of chips. Have you all seen this type of chip before? Right, good. Usually only have a very small number of gates in them. So this is a 7404 chip, only has 6 inverters in it. That's it. Didn't have anything more, right? So more complex designs were built up by connecting a number of these chips together. Now, it's a true fact that when I started teaching this course back in the 2000s, the class was using so-called breadboards, and I'll show you what a breadboard is in a moment. And you were given a whole pile of these chips, and your labs consisted of plonking them onto the breadboard and wiring them together and getting them to work, and showing that you could build a flip-flop by doing it that way. So you have come quite some way as well in going to FPGAs. So this is a photo of a small computer that was built with these chips. I can tell you that debugging these circuits was a nightmare because these wires, so the breadboard is basically an array of copper pins which all are connected on the same row, if you like. They're all connected to the same base. So all of the pins that you see in one row have the same, are electrically at the same voltage, right? So you use the wires to connect between things in order to be able to, am I right there, or is it the vertical ones? It might even be the vertical ones, because the way you see these chips, sorry? It's the vertical ones, is it? Yeah, the way you see these chips, it must be all of the pins in a column have the same voltage, going up or down, spanning on the either side of the chips there. Anyway, those wires, have any of you used these breadboards before? Right, so you know what happens when the circuit isn't working for some reason or other, and the challenge usually is to figure out which of these wires is broken, because one of the wires is broken more likely than not. Okay, questions?
Do I have to do that for Lab 6 back in the day?
No, you would not do that for Lab 6. I think doing something close to it on an FPGA is much easier, much quicker, much easier to debug, more likely to work when you've actually got the right design in there. Whereas these, you didn't know whether you had the right design or whether there was actually a physical error with some of the devices that you had there. All right, so in the 70s, early 70s, these chips had really only a few dozen gates in them usually. We talked about gates that had maybe, or chips that had maybe 100 gates in them as medium scale integration. Anything larger was called large scale integration. But you know, that's become utterly meaningless over time, this differentiation, because these days we have billions of transistors on large chips. So even the term very large scale integration, which began to be used in the 80s, has been covering a vast array of number of transistors included. But in principle, what has been driving this is the need for reliability, reduced cost, lower power, more performance, and increased profits for the people that are making these chips, Okay. So one of the problems with these devices that look like this is they're fixed, right? The only thing that we can do is change the wiring between the chips. So back in the early 70s, the notion of designing a programmable logic device began. And the idea was that we would use, have logic gates inside a package, and we'd use switches to connect between them and change the functionality. And the first of these was the so-called programmable logic array that exploited the fact that any binary function, combinational function, can be realized using a two-level and/or circuit, right? So we have a set of inputs, and that went through a bit of circuitry that would buffer, amplify those signals, but also provide the complement of each of those signals. So you see coming out of here, not just each of the signals, but also their complements. That would go into an AND plane that's programmable and produce sort of product terms that could then be summed together in this OR plane to produce a sum of products realization of the function that you wanted. So in more detail, this is what that looks like. Here we see a number of inputs, a number of AND gates, with some sort of programmable interconnection between the input wires that we have and the outputs of these AND gates. These AND gates could then be programmably connected to OR gates down here, and thereby you could build a number of product terms, as you see here, P1. The output here is the AND of X1, X2, X1 and X2, that's it. And that term could then be combined together with a number of other terms in order to produce a function output F1, right? There's a number of ways these programmable switches can be produced, and we'll talk about that in a moment. Another way of illustrating or representing the program that's been implemented for a particular PLA is just to draw a cross where there's a connection between an input and a term. So the fact that we have two crosses here means that this AND gate is computing X1 and X2, whereas this one's computing X1 and not X3, and so on. Similarly for the OR functions down the side here. So this is really just a schematic way of illustrating what the program might be that's in a particular PLA. So the next innovation actually did away with the OR plane and simply hardwired the AND gate outputs to the OR gates. This reduces the amount of programmable switches that are in there and thereby makes the design cheaper to fabricate and also faster. So the inventors of this particular technology, I dug up this photo that I remembered from my youth. I don't know whether I can easily access it though. So these are the inventors of PAL technology. They worked for a company called, I forget the name of the company now as well. And this is a photo from a National Geographic magazine article in 1982. And I remember seeing this photo back in 1982 when it came out. And these are the two inventors of the PAL, and these are the cars that the company bought them. Every 4 years, they renewed their cars for them. So very nice, very lucky fellows that benefited from their very clever design. And the clever design was eliminate the OR plane out of the PLA, which I think is, I don't know whether it's worth a Porsche 928, but that's a good outcome. don't know why that's not working. Shouldn't have shown you that photo. There we go. All right. More innovations that were introduced for the PAL were to put, after the output from the OR plane, is to add a bit of circuitry at the back here that we also see in FPGAs these days. You have the option to latch the output or to have it directly drive an output pin via this tri-state over here, or to send it back into the AND plane to increase the complexity of the signal that we want to compute. Right. So as for how do we program these programmable devices, there's a number of technologies that were developed over the years. The first ones relied on so-called fuse and anti-fuse technology. What they rely on are actually blowing fuses in the design. This is not a programmer for those. This is a programmer actually for the electrically erasable programmable read-only memory, which is has a floating gate which you charge and thereby then set a particular configuration into being. And since it's floating, there's no way for that charge to be dissipated. And so once it's programmed, it remains programmed until you clear it effectively. And typically that was done with ultraviolet radiation. In FPGAs, as you're familiar with, we use SRAM, which is fast, much faster than these other technologies, but it's volatile, which means that if you switch it off, we lose the configuration. And there are also FPGAs, for example, and complex programmable logic devices that are programmed using flash, which is not volatile, and it's even higher density than SRAM, but it's a bit slower. It's not quite as fast. All right, so I also wanted to just explain what a complex programmable logic device is. So we've seen what a PAL is, a programmable array logic. So that's just where you have a programmable AND gate, AND plane, but no programmable OR plane. Now imagine we've got a whole pile of these that we connect together via interconnects and lots of I/O as well. Digging into the detail of some of this, here's one of those PAL-like blocks, and it comprises numerous so-called macro cells. Here's one of those macro cells illustrated. It might have 5 to 20 inputs, something like that. A number of functions, maybe 10 to 20 AND gates, and maybe on the order of 10 OR gates coming out of it. We have exclusive OR gates here that can also potentially invert the output of one of these functions, and of course the circuitry to latch an input and then either send that function straight out to a pin or to send it, recycle it internally to allow it to be used as an input again for another cell. Okay, and I think you've seen this slide before, which is a very simplistic view of an FPGA, where we have a number of so-called configurable logic blocks, which are usually implemented as lookup tables or a cluster of lookup tables. In the FPGA that you have, I think there are 4 lookup tables per configurable logic block, and each lookup table is a 6-input lookup table that can be split into 2 5-input lookup tables, each with a separate flip-flop registering it. So there's 8 flip-flops per logic cell as well. And then the blue here represents the routing matrix that allows you to interconnect the configurable logic blocks. This is a fairly old view of what an FPGA looks like. In reality, a modern FPGA looks a little bit more like this, where you still have these relatively homogeneous regions where it's all just lookup tables and arrays of wires, but we have interspersed there these red columns that represent block RAMs. As you know, your FPGA has those block RAMs on it. And the blue, darker blue columns are so-called DSP blocks, which are just multiply accumulate functions. So they're faster than the surrounding lookup table logic because they don't need the programmable logic cells to configure them. They're already tuned to do 18 by 27 multiplications and have latches inside for words that are up to 40 bits wide, I think. And we also often have high-speed interfaces as well as potentially some microprocessors. And if you're doing computer engineering, you'll see some other devices later on in your degree where we make use of those microprocessors and the FPGA logic as well, the so-called programmable logic as well. So a lot of resources are hardened, so-called hardened in modern day FPGAs in order to speed those functions up. So particularly memory and multiply accumulate units. Okay, I'm almost done with this. So the problems with programmability is that a lot of area is sacrificed for the memory that determines what the configuration, the current configuration for the device should be. So that consumes quite a bit of space, and so FPGAs you can think of as probably being on the order of 10 times larger than a corresponding custom VLSI design would be if you didn't have all of the programmable stuff that's there. And because of this increase, because the area is dilated, we also have a slowdown in speed, which means that the clock speed is significantly lower. So high clock speeds for FPGAs these days are in the order of maybe 800 to a gigahertz, 800 megahertz to a gigahertz, whereas obviously we have VLSI circuits that operate at probably 5 times that speed. So if we want the highest possible performance and the smallest possible chips, then we have to create those chips from scratch, which these days normally starts with prototyping a design on FPGAs, proving that it's correct, validating the design, and only then using the same hardware description language description of the circuit and using that with appropriate compilers to generate a custom transistor layout for that chip. Okay, because of the design effort though, these chips are extremely expensive. You know, we're talking about tens of millions of dollars to start a custom chip design. And so that's only done commercially when the volume of chips that you're going to sell is going to pay for the design cost. And so we can really only justify that with very large orders. So only when you perhaps need 100,000 units or more does it begin to be commercially viable to go for a custom design. So examples though, I mean the same process though is used in designing all of the commercial off-the-shelf designs that we use every day that are programmable themselves, such as microprocessors, memory chips, GPUs, FPGAs. They're all custom designs ultimately. But because the companies sell millions of them, they can afford this investment in custom architectures. But if you're only designing a one-off solution to some problem, or maybe you're fabricating, you know, if it's, let's say, a satellite system that you're building, you're not going to be building custom chips for that one satellite. You would probably be designing circuits that will be implemented ultimately on FPGAs, because that's a much more cost-effective way of achieving a solution. And that probably is true for defense systems, but when we get to commercial designs like automobiles or smartphones, that is the scale at which we can then begin to afford to look at using custom chips to implement those. All right, if we go to a custom chip, there's sort of two main, well, there's a number of principal ways that they're manufactured. One is use so-called standard cell technology, where we have libraries of different sub-circuits. Here, the sub-circuits are the different types of gates that we want to implement, and we can plonk those at literally as we wish together. And what we're mainly concerned with then, or what the CAD tools are mainly concerned with, is how to wire those guys together. So how to place them optimally to minimize the wire distances, and also how to minimize the number of tracks we need to be able to implement the design. And that then is also known as application-specific integrated circuit design. But it's a relatively quick and dirty way of implementing a custom chip. A more elaborate way of implementing a custom chip is the so-called gate array technology, where the silicon chip manufacturer produces a silicon device with a sea of gates in it, like this, but none of them are connected together. They sell that then to manufacturers that will put the metal layer in to connect these together according to a particular design. And that then is the gate array technology that's known as a masked programmable design. Beyond this, I don't have a slide to illustrate it, this is what fabricating the metal layer in such a sea of gates design would look like. Beyond this, you would be laying out each transistor, and you use a completely different suite of CAD tools again to be able to then completely customize the layout of the silicon. All right, and that's about all I have on implementation technologies. I hope that gives you some sort of feel for what the potential implementations are, and mainly an understanding of CMOS technology and how that relates to the gates that you've been studying and the circuits that you've been designing. Are there any questions? All good? Right. Well, we can all go home. Unless you want to stay here. All right, so we have one more lecture on Tuesday, which is literally just a review, and I may be able to give some more insight into what the exam will be. I haven't looked at the theory paper yet. I'm currently writing the practical paper. So I know what that problem is, but I'm not going to tell you what it is. And I think that's about it. So do you all know that the exam is on the 14th, I think, and it's scheduled for the morning of the 14th? No, it'll be like 9 o'clock, I'd say. Be prepared for 9. It'll probably be a 9:30 start. But yeah, well, don't know whether those slides, they're from last year, those slides. So that's not entirely accurate, but I'll try and find out.
I have one question. So it's open book, but for the lecture slide, will it be available in the exam environment or no?
Well, you'll have access to the web CMS,
Oh, yeah.
but you won't have access to anything else. So if you want to bring slides along on a USB drive, that's fine. You can do that. I don't mind what materials you bring on your USB drive. You can fill it with the entire internet if you wish. Don't ask me to help bring it in or charge it up or connect it. And I'm not responsible for you knowing how to use the exam environment. You must know that by now. I've made that clear from day one that that's the environment you're going to be using. So please, if you haven't yet used it, go and use it. Make sure that your devices work in it. You can plug them in, get them working, try it out with your USB drives. Make sure that everything works okay, all right? It's the same environment you're going to be using, except that you won't have access to the internet. Okay? All good? Okay. All right. See you on Tuesday then.
Do you have any kind of general advice if you're interested in like microprocessors?
If you're interested in what?
Like doing like microprocessor and semiconductor stuff?
I still didn't quite understand. Circuits, did you say? Microprocessor circuits?
Yeah, like kind of that industry, like chip design industry over.
So I'm not sure what you're asking for, to be honest.
Do
I'm
you
sorry.
have any like advice for like kind of like courses you can take,
To do what?
Finish part two.
like chip design?
To do chip design. Okay, so I don't know what's on offer in EE, but I think that there would be more there. I'm probably as far as CSE is concerned.
Yeah.
We're not going to get any further into it. Whereas there are courses in microelectronics in EE.
Yeah, those are offered.
Yeah, so as long as you do the prereqs, I would, and if you're a computer engineering student, I would allow you to do them.
Yeah.
No problem.
I think they're offered in our course. You can do electronics and then microelectronics.
Yeah, are you comp-eng student?
Yeah.
Or, right, so you can do any elect courses as long as you do the prerequisites. And that's sometimes a little unclear because there are unwritten prereqs.
Yeah.
So a lot expect, for example, Maths 2A as a prereq, even though they don't officially expect you to have done Maths 2A.
Yeah.
So just be aware of that.
Yeah.
I think, have you seen the guidelines that we give as far as electives are concerned for computer engineering students?
The resources.
Yeah, under the resources. Yeah, I think I make it clear there that you should probably do Maths 2A if you do want to do more advanced electrical courses.
Like electronics, something like that.
Yeah.
Those electronics can go to the prereq.
I think for electronics you do need it. Like, I'm a little dubious or skeptical about some of it though. So when I was a student, I did an electronics course and it was highly mathematical, very, very difficult to understand. You know, all to do with Schrödinger's equations and so forth. And really, I don't think that you need to know very much other than for computer engineers, put it that way, that you can switch these guys on, you can switch them off. We don't really care about their analog operation. We really only care about their discrete digital operation.
Right.
But if you're, for microelectronics, you're probably designing circuits. at the transistor level,
Yeah.
and therefore would need to know a lot more about crosstalk and some of the finer issues that can arise,
Yeah.
especially at high frequency.
Oh, sorry, just to cut in. So then if we're planning to do electronics and microelectronics, is it recommended to do also Math 2A as an elective?
I think you probably should.
I heard that many.
Got it, I got it.
I think you'd be well advised to do Maths 2A. And I would always allow you to do Maths 2A instead of discrete maths. I don't care. You know, it's not a,
Yeah, everyone's
You should
already
have
done
told me
discrete
that. I would have
maths.
switched. I was like,
Why?
why am I learning discrete?
Oh, because it's like one of the first courses they tell you to take, and so like everyone's done it.
Because it's a year one
yeah,
course. so-
right. Well, maybe I should make it more clear that there is value in studying discrete maths. Don't get me wrong. And for the majority of students, discrete maths is a lot easier to handle than Maths 2A. But if you do want to get into the harder core advanced electrical courses, then you do need that Maths 2A background.
Yeah.
And, you know, if you realise that early enough and asked me, I would have said, yeah, of course, just do Maths 2A, that's fine. That's in lieu of discrete maths.
If you have any free
It's very hard to set it up that way in the uni, to officially say you can do either discrete maths or Maths 2A.
But they can do
Different levels, different outcomes, completely different successor courses.
I still got
What
one
you
or two
figure
elective
is you
left.
set up like
roughly.
an
I
elective
was
list
like,
of size 2.
I was like, what should I do?
It only has those
Yeah.
two ones, and you have to
Now
do
I know.
60 credit of those elective
Justifying it
lists.
to the university is
You can bring
impossible.
your flash
Oh,
drive,
right.
put anything on it.
I just assumed it was a
Impossible.
technical problem, but if
No, it's
if
not a technical problem.
talking to a university, then
No. Yeah, it's really hard.
what does Maths 2A teach you? Because I do. all
You
the-
can still do Maths 2A as a free elective,
Yeah.
of course, and therefore, you know, there's few restrictions, but if you'd come and seen me, I would have said, yeah, you do that instead. But I will make it more explicit than in the elective. I don't know whether the uni will like me saying it, but. Right.
I think
So
I've
yeah,
elective.
I would talk with have a look closely at what courses are available in the elect profile. We do have new staff in computer engineering, and we're hoping that each of them will develop an advanced elective.
Okay.
And some of those might become relevant. I doubt it though. They're probably not going to be in the chip design area or microprocessor design area as such.
Is hardware security one of those new courses?
Yes.
Yeah.
Mhm.
Because that one does look good.
Yep.
Because I think that's like one of the only like computer engineering specific courses.
Yes, but it's an elective. It's not a core course.
Yeah.
Not required. Yeah, but I noted a lot of comp eng students are taking it.
If we want to take electronics, do you reckon we can just learn the content of Maths 2A ourselves instead of taking a course?
Look, to be honest, you'd be well advised to go and talk with the relevant people in electrical engineering. So the
Yeah.
convener for
For electronics.
microelectronics.
Yeah.
So second year electronics you've got to do anyway. It's the third year electronics where it begins to be a problem. There's a 3106
Yeah,
course. I think.
Yes,
316.
that's the one.
Is that electronics?
Yeah.
That's
Yeah.
electronics. The level 2 is analog one, the 2123.
Yeah, yeah.
And the 3106, they expect you to have Maths 2A under your belt, even though it's not a prereq. So if I were you, you would just argue, you know, I want to do that course. Oh, you haven't done Maths 2A. But Maths 2A isn't a prereq. And put the problem back onto them. They should be listing it as a prereq. They're not listing it.
I think it was at one point, but like checking it in recent times, it's not there anymore.
Yeah, they remove it from the handbook.
I don't understand that. When I redesigned or tweaked the computer engineering program 2023 for the 2024 version, I approached electrical engineering and wanted to add a whole pile of interesting third third and fourth year courses, most of them they wouldn't allow me to add because they said, we expect our students to have Maths 2A as a background.
Oh.
Okay.
But then Math 2A is only in term 2, right?
Straight through.
Oh, term 3.
That's 2B, I think.
Oh.
Yeah, but it's a second year course, and
Yeah.
I'm talking about third and fourth year courses.
Where does Math 2B fit in?
2B,
Yeah, because that is a
I don't know what isn't that offered every
2B
term?
is done like linear algebra and stats.
Yeah, okay.
So that's
So
more
you're
for like-
asking about the content or when it's offered?
Yeah, I know when it's offered. I'm taking it next term.
Right.
I just don't know what it's a prereq for or like what it's used for.
Well, again, for our courses, it's no prereq. But if you wanted to implement AI algorithms, for example, you'd need to have that linear algebra background.
Okay.
Mm.
That makes sense.
So we could do, because when I look on the handbook, it says that the discipline electives are like the preset ones or like level 3 comp courses and above.
You can do anything that's a discipline elective. I'm not particularly concerned as long as it's at the right level and it's technically relevant to the degree.
Okay.
So, you know, if you wanted to do control, go and do control. If you want to do more DSP, go and do more DSP.
Yeah. Sounds good.
Oh,
Mm.
awesome. Okay.
Yeah.
That's good to know.
You may have to ask for permission to do it, but I don't think, well, I certainly wouldn't stop you from doing it. And I don't think anybody else who would follow me would stop you.
Awesome.
Okay?
Yep. That's good. Cool.
Okay.
That's good to know.
Good. Good. I didn't know that it was so restrictive or that it feels so restrictive. So maybe maybe I need to be more explicit and say, look, you can do almost anything, just as long as you've got a good justification for it. I've had to knock a couple back lately. There were some that wanted to do courses that I felt were at too low a level. You know, when you read the description of the course, it's just not really technically challenging. And we're expecting technically challenging courses appropriate to the level.
Is the general path just like email you, this is what I want to do? Yes.
In the first instance, you've got to see the nucleus and discuss with them what do you need to do to enrol in that.
Okay.
So you're on their horizon, and they'll probably say you have to get approval from your director of studies.
Yep. Sure.
Okay?
Yep.
All right.
This is awesome because I've been like looking for more discipline electives to do because I don't know.
Yeah, look, I know computer engineering has been a little bit thin on the ground.
Yeah.
We're aware of it.
Yeah.
We need to do something to improve it.
Yeah.
Yeah, so hopefully these new members of staff will offer new things.
Yeah. Yeah.
All right.
More information.
Okay.
Can
Right.
I send you the Math
All
2A
good?
this
2A
year?
term 3.
Yeah.
Thank
I'm
you.
gonna do it.
No worries. See you guys.
I was looking for other courses.
Because I want 3 electronics.